they are quite well aligned in this picture, and we interpolate these, and then we are basically correlating these lines. But the picture is not really as rosy as it seems here, because we are using uh, we have RC oscillators on these chips, so which are quite inaccurate. They are cheap, which makes the RFID tags cheap. But an after effect of that is, though we intend all of them to be exactly aligned, or say if I'm transmitting once per second, then not all of them identically have this interval exactly at 1 second. Maybe one of them is 995, 987, and so on. So that creates like, so there are collisions in between, and you tend to, this is what I've already said, you tend to lose packets, and you can still interpolate, but the interpolation and then the correlation would not really represent what you're actually looking.
So why did you packet loss?
Because the intervals are different. So though I intend them to be exactly, say I'm transmitting at once per second, and I intend all the transmitters, like 2 in this case, then I intend both of them to be transmitting exactly at once per second. But there are variations because of this RC oscillator, which makes one transmitter 995 millisecond after, like once after 995 milliseconds, whereas the second one is say accurate and it transmits once per second. So it's these variations which make them overlap in some places, and which results in collision. So as a
just out of curiosity, how long are each transmission?
It is 400 microseconds.
And each transmit once per second?
No, each in our, I mean, for these experiments, each is transmitting 16 times. 16 transmissions per second.
What collisions do they have, and blah, 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 right? And they each have a random frequency, ranging from 990 to 1010.
It is like those homework problems.
Did you do this, and did you sort of work it out, what you should expect in terms of packet loss?
Yes. In fact, I mean, before we, so that's what we precisely decided
What
about
in your thesis?
No.
Why not? That seems important.
You can add it in your thesis.
I'll add it. I still have some. So there was this is really the formula that the MATLAB function uses, the Pearson's correlation coefficient.
That's fine.
So
Okay, so just go back to the formula.
Yeah.
Xi and Yi, what are they?
Those are the measurements of for X and Y.
Yeah,
Oh,
what are they? What are X and Y? What's that, like Xi, what is Xi?
So X and Y, so basically X and Y are the random variables, and Xi
What are your,
and Xi and Yi are, so we are when we sample these random variables, when we take n measurements of each.
Yes,
Are
but
they
okay.
RSSIs or are they?
Okay. Yeah, those are RSSIs. Received signal strength indicator.
And N is the amount of
Number
samples
of
I'm going to
measurements.
average for a particular location.
No, for the duration of the experiment. So,
But each data point is already averaged over different.
so
Yes, is this for one location where you make a bunch of measurements all within,
yeah.
like,
So if I'm doing it in the orbit room, and if I did it over a period of say 5 minutes.
No. You described where you went to location P1 or P2, and you stood there and you sort of waved your wand around. Is this what you did for one location with one wand wave?
No. So, yeah. So those were for when I've completed my transitions over this trajectory.
To look at the correlation.
Okay, so what is
So
Xi?
because I've said that these are correlations in space, right? So
But what is Xi? So it's an RSSI.
yeah.
averaged, like,
Averaged
in
over.
the ith value, X is for one transmitter,
Okay, so
Y is for the other.
so xi, so one of
so
them
what
would
is
be
XI?
RSSI here, x1, x2 would be RSSI here, and so on.
So, okay, so X1 is transmitter 1 RSSI at position P1.
Yes. Yeah.
Averaged over,
Right.
the RSI is averaged over, you're
Yeah.
waving the wand around
Yeah.
the stick.
Yeah.
Okay. So how many locations did you use?
Locations you mean?
Did you
What was the
use
number of
this-
n?
It's
Well, yeah, okay. Yeah. So do you really use discrete locations? So you said, I go to this location, I stand here and wave the stick around for some amount of time, and then I walk over here, now I wave the stick again.
no. So what I really did was I had these transmitters and I was just walking around
Okay.
with like moving the transmitters around.
Okay.
So I mean that's a simplification of what you just described. With me
Well, it's
taking
yeah, it's
taking the measurements here, then I move here, I put the batteries again. I mean I'll have to take out the batteries, put in the batteries again. So it's a simplification of the same procedure.
Your picture before gave you the other impression too.
Yeah.
It gave us the wrong impression.
I should have clarified.
Let's see the results, because I think that will allow me to clarify my.
So how did you calculate X bar or Y bar?
I mean, for these experiments, it's all really I had to do was, I mean, after I have processed the data, I mean, after I have done this interpolation, which I described, I just had to feed it to the manual function, which precisely gave it the interpolation.
So how big was N?
So the duration was about 5 minutes, 16 transmissions, about 5,000 measurements.
Right, so I think I'll just ask my question rapidly.
Yeah.
You're going to calculate the correlation coefficient for what? What's going to be the dependent variable over which you're going to report a plot of correlation coefficient?
So over distance.
Distance being separation between transmitter 1, transmitter 2,
And
and trying to measure.
So, okay, I think this slide is really not
I mean,
clear.
there's a distance that you're walking here, right? You've got, so here's my question. You've got this stick and it has transmitter and transmitter, and there's some base station that's
Right.
that's going to collect.
Right.
And you're walking, and you're probably walking, you're doing this.
Mm-hmm.
All right, I've moved 5 feet. All right,
Mhm.
that's 5,000 data points, whatever. Right?
Mm-hmm.
Now, question one: when you're doing that
Mm-hmm.
for this location,
Mm-hmm.
this is the discrete question you asked. You're doing this.
Mm-hmm.
Was this 1,000 data points, and you got average over 1,000 data points to get an X and a Y?
No. So the way it was, so say you move from here to there.
So continuous. I got
Continuous.
5,000 data points.
So when you move from this position to this, and when your transmitters are transmitting 16 times per second, and then by the end of that session, you have 5,000 data points.
Right.
Yes.
And the RSSI variations that you see over this transition is what we are correlating.
Right. So in the end, you're just going to get one number.
Yeah, and then you get one. But to be
In one number for row.
Well, yeah, row is just going to be 0.47.
So there are more like intricacies to it. So as I'm moving from this position to that, there are two effects as I've presented them in a previous slide. There's the slow fading and the multipath fading. Right. So we separate out these two. So basically, I take a moving average of, as I'm moving from this position to this, I take a moving average of say 100 samples. Say 100. I'm saying 100 samples just as an example. Say over 100 samples, the slow fading is almost the same. So after every 100 samples, say the slow fading changes. So it's really, say over these 5,000 measurements, say after every 100 samples, the slow fading is changing. So I really have 550 samples for the slow fading and the rest of the class.
So now I think you've just introduced one more thing which you haven't told us about, which is this moving average that you're doing.
Which I'll go.
But how is that going to impact your definition of Pearson's coefficient?
It's not. I mean, the only thing that changes in the two is the number of samples you have.
Which is n.
Which is n, yeah.
Which is why we asked you originally, what is n? And you said it's 5,000 again.
Well, maybe it's 50.
It's delta t, where delta t is the width of your
Can we
moving
can
average.
give a rough estimate towards the end there?
Now I feel
So-
what's happening.
You're back here?
Well, I think I know what he's doing.
Oh,
The explanations become.
I was happier at 5,000.
So can you give
But
a
from
rough
that would
estimate
be
towards
one,
the end?
one
What's the value of
value
n?
for the entire thesis.
Well, maybe you said maybe you're doing it for different positions, different spacing,
Yeah. Well,
blah, blah, blah.
Okay, so I think the better answer for your question would be
n is the width of your averaging window.
So RSSI, you know what the units, like, is it
it's
measured?
dBn.
And is it produced in like one steps?
It's
Is it
the
in
resolution
inches?
is half a D. I mean that's the lowest. Okay, so this is the location. This is our orbit room, and this is how usually the base stations were placed. So you see three laptops here. There are two receivers attached to each laptop. There's a laptop here, one in the other corner. So they roughly form an equilateral. And we had 6 receivers, so 3 laptops and 6 receivers. That's me. So this is how I usually used to walk. So this is the stick I'm talking about, and it's this stick that I'm moving on. So maybe this is the distance over which it really moves. They are put in the bag so as to not ruin the antennas around the other side. Oh, okay. I think this could be an explanation of your question, something like that. So when I was doing, so this is this data is it was collected for one of the experiments when I was moving in circles. So this is the data at one of the receivers. So as I'm moving close to the receiver, you see the size going up, and as I'm moving away, it's going down. And since I knew, I mean, I completed 6 circles, so you can see roughly like I've almost completed those 6 circles by the end of the experimental duration. And it was carried over a duration of 5 minutes.
Every data point there is a sample, and that's going on while you're doing this.
Yes, yeah, yep, yep. And this data was collected, as you can see, when the transmitters were transmitting at 16 times per second.
And the about every 3 centimeter is the separation of the stick relative to itself as a
no, it's
or as relative
it's
to you moving.
relative to me moving as the transmitters were transmitting. So this is what I hinted to when I was trying to explain what I'm really doing. This has been derived from the previous data. It's by taking the moving average over 2.5 seconds. Now 2.5 seconds is not really hard bound. It could go to 3.5. The important thing to note here is the x-axis here, and the horizontal axis here is the samples and not time, which again I'm emphasizing that time is not really very relevant. It's just the samples that we are correlating.
When you say moving average, are your windows overlapped, or is it?
So it's a sliding window.
But sliding by
a
one
sample.
point.
Yeah.
Right.
Okay, so it's 50,000 samples.
5,000 samples. Oh, 4,800.
5,000. And it's 16 samples per second?
16 samples per second. So
like
since it was
55
done over,
minutes, right?
yeah, 5, 6,
Alright.
4,800.
So what, are you gonna explain this kind of surprisingly consistent behavior? Do you have an explanation? Like, it looked like about once per second you have about a 10 dB gain. I mean, it looks very distinct. Maybe it's just random jump.
No, because that is dictated by how I was moving, I mean, what my trajectory was and how my distance is very. So, I mean, that's why you have so consistent.
If you help us.
So I was moving in circles.
Okay, so you're coming back.
I'm coming back, I'm coming close to it. That's why I said, so this is when I was closest to the receiver, and this was when I was farthest.
And then
So,
So then you
so
add
I,
this one
yeah,
more time.
so, yeah.
10,000 samples is about one circle, and you made about 5 circles.
Yeah, about 6
1,000.
circles. Out of 1,000. Less than 1,000. Less than 1,000, in fact, I said. I mean, close to 1,000
Close to
for a circle.
Okay, so all right.
Did I answer you?
Yeah, that's good. Right. So you have a good explanation for this technique.
Usually we need to make our students run in circles, so.
So how big was the circle you walked around? Your
About
pictures were not, your pictures of the orbit room and what kind and where the antennas were are not very clear. So, yeah, well, the previous one, like I can't really see where the base station.
yeah, you're right. So these are really the receivers and the small antennas, which are about 8.5 centimeters in length.
Usually pictures are nice, but actually a kind of a little diagram of the room, the antennas, and what your trajectory was around the room.
Yes, I should have thought about it.
Yeah, it will be better.
I'll make sure that I put it in the thesis though. So this is the other part of it. Let me. So this was the data that I presented to you. This was derived from that. This is the multipath variation. Again, as you can see, it's samples, and since it's the same experiments, it's the same number of samples. The variations are about 7 to 18 guidance. Yeah. Let me magnify this, and this is what they really are. So 6 samples is approximately a wavelength, and these are the, I mean, if you really look closely to the multipath variations, this is what it is.
So this notion that 6 samples is about half a wavelength it's kind of a really a loose ballpark, because the sample is a wavelength with respect to your personal motion, which is not particularly
Consistent.
Yeah, right, consistent.
In fact, that's precisely the reason why I showed you that graph. I mean, though there is a little inconsistency to that, it's not a lot. So, I mean, that's why, I guess that's why you wondered how this data is so consistent.
Yeah, because because it's over some large scale motion right around the circle. Right?
Yes.
Okay.
So let me present some results after I hope that the way we did experiments is clear. Before I move on to experiments with 2 transmitters, I'll try to explain the results of a calibration measurement that we did to verify whether the way we were doing the experiments and whether the software that we developed does really give us the numbers as expected. So the experiment was, we had a single transmitter. It was transmitting at twice the nominal rate, and every alternate packet was, so basically the entire data was separated into alternate entries, and these 2 entries were really correlated. So it's virtually correlating the same variations with themselves. So the correlation was expected to be 1. This is, so as you can see, the slow fading is really very, very close to 1. In fact, it's almost 1. And to see if the way I was moving has any effect, there were 3 paths that I took. The first one was circular, for which you've already seen the data. Then there was a random, so random path was really, what I mean by that is a non-periodic path as we had in the first one, and a straight line path. So if there are receivers facing the 4 corners, I was moving along the length of the and similar for multipath fading.
And what are you correlating here? You're correlating the R's of something value.
We are correlating the axis.
Are you correlating the moving average to RSSI?
So the moving average to RSSI is the slow fading. So
You are.
So what we really are correlating are 2 curves like these, 2 variations like these, 2 signal level variations, and 2 signal level variations like these. So these are the and so those after
So what? Are you sure you know what that means?
Basically, he's not capturing. This is like it's not capturing fast fading. He's separating out the whole fast fading part. Just looking at two samples that are 80 milliseconds apart, essentially, which are each coming from average. But understand that your samples that you just record there, the windows overlap like that much.
yeah.
So I expect that there's a heck of a lot of correlation between those two samples.
So there is
Your moving average window, you said was on 100 data points or 1,000 data points.
Oh, it's just one transmitter.
This is just one transmitter. So it's
Correlated
transmitter
transmitter,
virtually
and he's doing-
correlated. He's in fact it's practically correlating.
Even and odd samples
Right.
of the time average output.
Yes. Yes.
Right.
And what was the purpose of doing this experiment? What was the purpose of doing this measurement with a single transmitter?
First of all, to confirm, to basically to validate both our software and the measurement experiment design.
So you're calibrating yourself and your
Exactly, we are calibrating ourselves. So
Had
had this not been one, then we would have known that there's really something wrong. We cannot go on with other measurements.
Alright.
So
if-
this tested the fact that we had no mistakes in the software, of course. What else did it test, which was an important assumption that we wanted to verify?
That we had like enough samples when we are taking the measurements
Enough samples for what?
to capture the multipath variations.
Okay, so what part of the software were we worried about that for which the samples may not be enough?
For the multipath part of it, I didn't get it.
So we did that because we did something in the software, and we were concerned that that particular operation in the software would do its job correctly. Which operation was it?
The interpolation.
The interpolation, that's right.
Yeah, so that's
And why do we need the interpolation in the software?
because we're really so basically we have like samples here, samples there, and samples at different positions, and we want to see if these variations over this trajectory are really the same. So since we do not have a continuous waveform, I mean, since we do not have exactly the RSSI variations at infinitesimal positions like throughout this trajectory, that's really why we are interpolating. So in fact, when I have said that there need to be bounds on this, that's, I mean, one thing I wanted to emphasize here, which I think I did not, was when we say that we have to have a bound on this, if we interpolate over these samples which don't really exist in space, we are screwing up things. So for our measurements, we've taken like, we have set a bound on 2 samples. So, and that's because by interpolating over 2 samples, which is at 16 transmissions per second, is about interpolating over approximately 5 centimeters. That's even less than a quarter of a wavelength. So we knew that despite an interpolation over 2 samples, 2 missed samples, we are not really affecting the correlations or not introducing artifacts in our measurements.
Also, when you're doing your interpolation, is it forward-backwards interpolation, or is it just forward
It's-
interpolation?
It's a quadratic spline, so
So forward-backward.
I don't know what
You're taking, go back, take a picture. Are you taking data from the left half and the right half to fill in the middle?
Yes. Okay, so these are the calibration measurements and data as expected. And these are really the readings from when we had 2 transmitters during the experiment. So this is the slow. These are the correlations from the slow fading variations, or these variations for true transmitters.
Okay, so now they're separated by 25 centimeters or so.
The separation varies all the way from 8 centimeters to 25 centimeters. And the correlations are, I mean, they were expected to be high because if I have these two transmitters here and the receiver, I mean, unless it's really comparable to the obstacles between transmitter and me, it was bound to be high. This was a result which really surprised us because we had really expected we were expecting this to.
So the transmitter separation is like the distance you separated them on this stick.
Yes, that's
And so here you just looked at the slow fading variation.
yes,
And
for
then-
in this.
Okay, so the correlation's really high. I'm surprised. Maybe I'm not.
What he's done is his time average.
Yeah. Okay, all right, let's go to the next one now.
I mean, when we did the measurements, we were expecting them to really be very high when they are close and then go down, but they were consistently low.
Well, so first off, how are you calculating multipath fading?
So, I've already said that I took a moving average over this data. So moving average over 2.5 seconds. So those many samples comprise of this slow fading component, and basically we subtract this from deduct this from those variations, so we get this.
So that is a subtraction of your original data minus your time average.
That's right. That's right. So.
And then you correlated those by using your correlation formula, using zero mean at this point.
Yes.
As though sample one for transmitter one lines up with sample
That's
two.
right. That's
right.
Yeah.
So somehow the things are supposed to be highly correlated at half a wavelength or less than half a wavelength, right?
Mm-hmm.
But so that's sort of like around 15, the half a wavelength.
Yeah. Half a wavelength.
So did you try? Is there any reason you didn't go to 5 or 3 centimeters?
Yes. So I did go up to like 8. This is 8 centimeters.
Yeah, but why didn't you go to 5 or?
There were two reasons for it. First, this 8 centimeters is about a quarter of a wavelength, and we had like papers to compare these results with. So I mean, this was a really good ballpark for us to know that if at all our measurements here are right, if they match the measurements that we've seen in papers published before, then they ought to be right. So I mean, this is at 8 centimeters. I could have done it at 6 centimeters or so, which in fact is the next measurement. It would not change correlation. In fact, we expect the same trend. Because that's really changing the sample at 16 times per second. Because the difference is just 3 centimeters between two samples.
Okay, so you, 3 centimeters between two samples. Oh, because of the 16.
Because I've already said that the variations are about 5 to 6 dB, so it's maybe 3 dB. So you can take like give or take a dB.
So somehow, like if you could have somehow physically got to 0, you should be back to 1 transmitter, right?
Sorry.
Like if you could physically have had the 2 antennas like very close to 0,
Yes.
what would you have expected? Say 1
Consistently low. I mean, correlations low as.
Kind of explain. You guys have thought about this? All right.
Yes. So, I mean, this was much and I mean, we were anticipating something else, and this was quite astonishing. So we took some more measurements to see what. So basically, our hypothesis here was maybe as these two antennas or these two transmitters come close to each other, uh, though they are seeing a similar multipath, they are also getting electrically coupled as they come close to each other. So what I'm hinting towards is the transformer principle. So it's coming close to the first antenna's reactive field, and uh, it takes away energy from that field, and basically there's a coupling. So the hypothesis was it's that mutual coupling between the two antenna, which is um, giving us low correlations than expected. So the idea was if that is the case, the correlations should increase if these antennas are detuned in the sense both the antennas are, when we did the measurements, were exactly matched for 911 megahertz. I mean, they both were transmitting and receiving at 911 megahertz. The transmitters, in fact, there were no transceivers, so both were transmitting at 911 megahertz. So if we snip these antennas or detune these antennas, as I've already said, then they should absorb or steal less energy from its neighboring transmitter. And uh, after I did that, so in this experiment, what I really did was, this is the place where all the other measurements have been taken. I kept snipping these antennas by a centimeter in steps. So this is the place where it was snipped by centimeter by centimeter, and eventually the length of the antenna was 1.5 centimeters. So these were really very small antennas. And
You snip both antennas or just one?
both antennas. In fact, I've also looked at the trend when only one of them is snipped. So I've looked at the trend when the difference between the two antenna length is about a centimeters. So it still follows a similar trend. In fact, I can show you the graph. So the reason why we have a dip here really is because the impedance of these antennas, when the antennas were cut at the right length. Let me rephrase it. So when these antennas were designed by Professor Banerjee when he was doing it on the spectrum analyzer, that was really just one antenna. But the presence of the other antenna basically detunes or yeah, I think that's good enough explanation. Detunes this antenna. So initially the antenna is longer than what it should be. So after snipping it by a centimeter, that's when the correlations start going higher, because now the energy absorbed by the neighboring transmitter or being stolen by the neighboring transmitter, that decreases as I snip it more and more by a centimeter, and eventually eventually when I have the antenna length at 1.5 centimeters, I see correlations as high as 0.5. So this was quite interesting. The antenna separation, as you can see, is about 6 centimeters. The slow fading correlation were high as expected, as I've already shown you for the normal antenna lengths. And with that, I'd like to conclude. So slow fading correlations, since they were high, they could be used in localizing co-located transmitters. The multipath fading can be investigated for mobile phones, because the constraint there has been, since mobile phones are like very small, you cannot place two antennas really very close to each other. So, and with a small correlation. So from our measurements, since we find that the correlations are not really that high, maybe those could be investigated. And if at all multipath fading has to be used for localization, then detuning the antenna might be a solution. So what's next? So most of my measurements were taken in the orbit room, which is not really a practical scenario. So a better place would be to do it maybe in core, or PCC would be a good location. And that's it. Thank you.